So, you want to know the one question that separates the top 1% from everyone else? Well, let's get right into it. Okay, let's be real. There is a question in chemical kinetics that the CUET loves to throw at you. It looks simple. In fact, it's designed to look easy, but it's actually a trap. And honestly, it's the #1 reason I see students watch their dream rank just slip away. You know, this trap is hidden in plain sight, right inside the integrated rate equations. The people who set these exams, they know that almost everyone overlooks one tiny little detail. But that's not going to be you. After the next few minutes, I promise, you're going to see this trick coming from a mile away.
All right, let's break this thing down. What even are these equations, and why are they so darn important for your rank? Think of it like this. A normal rate law tells you how fast a reaction is going right now. It's basically a snapshot. But an integrated rate equation, oh, that's a time machine. It lets you predict the concentration at any point in the future or figure out how long a reaction is going to take. It gives you the whole story, not just one picture.
First up, we've got the zero-order reaction. And its signature move? It's a dead simple straight line. Let's see what that really means for you.
So what does zero order even mean? It just means the concentration drops at a steady, constant rate. Imagine a car on cruise control. It's not speeding up, it's not slowing down, it's just going. That's a zero-order reaction, a simple, predictable, linear drop over time.
And here's what that looks like on a graph. If you plot the reactant concentration against time, you get this perfect, straight, downhill line. This is its visual fingerprint. If you see this graph on your exam, your brain needs to light up and scream, zero order.
Now, you really need to pay close attention here, because this is where the trap starts to get set. Let's talk about half-life, the time it takes for half of your starting material to react. For a zero-order reaction, the half-life actually depends on how much stuff you start with. If you start with more, the half-life is longer. Remember that. It's clue number 1.
Okay, now for contender number 2, the first-order reaction. And its whole deal is the complete opposite of what we just saw. Its entire game is about one single thing, being constant.
So the equation looks a bit scarier because of that ln, right? The natural log. But all that really means is that the concentration isn't dropping in a straight line anymore. It's dropping exponentially. Think of it like a bouncing ball that loses half its height on every bounce. It drops really fast at first, and then the bounces get smaller and smaller.
So if it's not a straight line, how do we get one? Well, we have to be a little clever. Instead of plotting the concentration versus time, we plot the natural log of the concentration versus time, and when we do that, boom, there's our signature straight line again. That right there is the key graphical test for any first-order reaction.
Okay, I want you to actually pause and think about this for a second. If a half-life is constant, let's say it always takes 10 minutes to cut your material in half, how much is left after 2 half-lives? That's 20 minutes. Don't just guess, think it through. Did you get it? The answer is 25%. After 1 half-life, you've got 50% left. After the second, you have half of that. And the reason is right here in the equation. The half-life of a first-order reaction is completely constant. It doesn't care if you start with a kilogram or a single gram. The time it takes to have it is the exact same. This is the biggest difference, and it's the key to everything.
All right, it's time for the ultimate showdown. Zero versus first order. Let's put them side by side so you can see exactly how they're different.
Let's run through this nice and quick. The rate law? Zero order doesn't care about concentration. First order is directly tied to it. The graph? For zero order, you get a straight line with just concentration versus time. For first order, you need the log of the concentration to get that line. And the big one? Half-life. For zero order, it changes with how much you start with. But for first order, it's always constant. And finally, just look at the units of K. They're totally different, which, by the way, is our next big shortcut.
Speaking of units, this is another classic exam question. But I'm telling you, it is the easiest one to win if you know the secret. Let's master this units game.
All right, mini challenge time. Picture this on your exam paper. They give you a K value with this unit. No other information. Just from the unit, what's the reaction order? Go on, lock in your answer. The answer is first order. See, you didn't have to do a single bit of math, did you? The clue is right there in front of you. That unit per second, or s to the -1, is the unique signature of a first-order reaction. That's what I call easy marks. Here it is, clear as day. Take a screenshot of this, write it down, whatever you need to do. For zero order, the unit for K is moles per liter per second.
For first order, it's just per second. This is a free point on the exam, but only if you know it.
And that brings us all the way back to the beginning. The number one trap I told you about, it's not in some complicated math problem. It's right here. It's in the half-life. The examiner will give you a table of data and ask for the order. All you have to do is check the half-life. Is it staying the same? It's first order. Is it changing? It's zero order. That's it. That's the whole trick.
So, let's do a final super fast recap. Ready? Zero order, straight line decay, and the half-life depends on how much you start with. First order, exponential decay, but its half-life is beautifully constant. And if you're ever stuck, just check the units of K for a quick and easy win.
But look, today wasn't just about reaction orders. It was about a method, this whole compare and contrast idea. So my last question for you is, where else can you use this? Thermodynamics? Organic chem? How can you put two confusing topics side by side and focus only on the key differences that the exam actually tests? Because that's not just how you answer one question. That's how you build a winning strategy. Now go ace that test.